Good day, everyone. I'd like to welcome you to the start of today's webinar titled Fuel Cell Electric Vehicles, the Other Electric Vehicle, brought to you by the Center for Advanced Automotive Technology. I'm your host for today's webinar, Mike Lasecki. I'm here at the Maricopa Community Colleges in Phoenix, Arizona. It's our pleasure to bring this interesting topic to you. I want to welcome you as participants from across the United States. We have people from Michigan, Georgia, Texas, New Jersey, Illinois, Arizona, Ohio, Idaho, New Mexico, Kentucky, Maine, and the list goes on. And it's my pleasure to welcome people from outside of the United States, from Poland, Italy, Mexico, India, and from Fiji in the South Pacific. So thank you again. It's clear that this topic has widespread interest, both for its technology and for its workforce preparation needs. Let me advance to the first slide, and it'll be my pleasure then to introduce our presenters today. Joining us is Nelson Kelly. He is the Assistant Director for Energy and Automotive Technology at Macomb Community College. Nelson, I wonder if you would come on the line, please unmute your microphone and say hello to everyone.
Hi, everybody, and it's a pleasure to give this seminar today. I'm looking forward to going over the topic with you.
Thanks, Dr. Kelly. You've worked at GM. You were in the GM world for quite a while and had a lot of technical publications and a number of patents as well.
Yes, I spent 35 years there and retired, played a little bit of golf, and decided there was life after GM, so I came to Macomb Community College and started teaching in an electric vehicle development program and found that very rewarding.
Well, thank you, Nelson. Thanks for joining us today. Your experience and expertise is really appreciated. Also joining us for the second part of our presentation is John Prilla. He's a professor at Rio Hondo Community College. John, welcome today. Would you say hello to everyone? Unmute your microphone.
Hi, how are you doing? I'm glad everybody could attend this, and I'm surprised we got people from all over UK and down in Fiji, and I'm hoping that all this information we're about to present to you will be of some use to you.
Thank you, John. I know that you're, in addition to your work as a professor, you've been there for, I think, about 18 years now at Rio Hondo College. You, in 2015, were awarded a grant from the National Science Foundation to develop an associate's degree for fuel cell technician program. That's real honor. I know a lot of competition for those awards, so congratulations on that.
Well, thank you very much. We've also had other awards come into us. We got the California Community College Green Instructors and the Outstanding Program for the same type of awards for the green technology.
Now we're talking. That's great. Gentlemen, I'm going to take us forward to the first slide, and I'm going to ask Nelson. Nelson, would you review what our outline is for today and just go ahead and take over?
Sure. Thanks, Mike, and congratulations. You did push the record button, so I think we're in good shape. I'm going to do the first part of the presentation, and I'm going to start out with a brief introduction to what the Center for Advanced Automotive Technology, which I'll call CAAT, is. That's here at the Macomb Community College. I'm going to talk about how we got to electric vehicles and the different types, how we can make electricity using electrochemistry, how we can make electricity using proton exchange membrane fuel cells, which are the way we do it aboard vehicles, fuel cell electric vehicles, how we can store energy to move the vehicle on fuel cell vehicles, how we can store hydrogen as the energy source, something about zero-emission vehicles. That's going to be very important. That's a driver for making fuel cell electric vehicles and other types of electric vehicles, and greenhouse gas emissions and protecting the planet. This is what we're trying to do with this new technology. And finally, how hydrogen has a synergy with renewable energy and fuel cell electric vehicles. John Prilla will do the second part, and he's at ground zero for where this technology is really taking hold and where in the last couple of years there's been very, very many exciting developments. This seminar would be very different if we gave it 2 years ago than it would be now. It would be much less interesting, I'd say. Just a little bit on my qualifications. Mike said a few things about this. I've taken a lot of chemistry courses, and it's starting in high school, and that's why I really got interested in it. High school chemistry and physics were a good start on what I'm going to talk about today. And I recommend other people who are interested in technical fields and even the automotive industry start with those. And we'll say a little more about that later. I then was a research scientist at General Motors in Warren, Michigan, just down the street from where I'm at now for a long time, 35 years. Retired, came here to Macomb Community College, and I'm very happy to be here. I was an adjunct instructor at first, and now I'm at the CAAT office, the Center for Advanced Automotive Technology, where I'm Assistant Director for Energy and Automotive Technology. My background includes a lot of work on the bad things that cars can do. Tailpipe emissions that cause smog, other types of emissions. And then I got into a field that I thought was a lot of fun and more interesting. How to try to prevent some of these bad environmental effects by using hydrogen, trying to have a hydrogen economy and fuel cell electric vehicles, and especially renewable hydrogen production and battery charging. So that kind of gives an idea where we're starting. The CAAT, the Center for Advanced Automotive Technology, is located at the Macomb Community College South Campus in Warren, Michigan. And we became an ATE, Advanced Technological Education Center, in 2010, which is funded by NSF. And our four-year partner is Wayne State in Detroit. We got the grant renewed in 2014 for three more years. And our main mission is to develop and disseminate advanced automotive technology curricula. In other words, any emerging technologies like connected automated vehicles, lightweight materials for vehicles, which every major manufacturer is working on, and electric and hybrid vehicles. And that's what we're going to be talking about today. And that's a very important aspect of trying to develop curricula for the next generation of automotive technicians. The other aspect of this, which is really important, is to provide outreach to middle schools and high school students to get them interested in STEM, science, technology, engineering, and math, kind of like I did. And like I say, in high school is where I started being interested in chemistry, which you'll see is pretty important to understand the running of a vehicle, both the current crop of vehicles and then the future vehicles. So let's start out with the current crop of vehicles. Where does the energy come from that you probably use to drive your vehicle to wherever you're at today? It probably used an internal combustion engine, abbreviated ICE, that burned gasoline as the fuel to make heat that expanded the gases in the cylinder to create mechanical energy that moved the vehicle. And a chemist might write this as octane, 8 carbon atoms and 18 hydrogen atoms, plus just the right amount of oxygen, forms carbon dioxide, water, and makes heat. So these are the reactants, these are the products. This is what comes into your car, this is what goes out the tailpipe, and this is what drives the car, the heat, which is converted somewhat into mechanical energy. Notice each carbon atom made a carbon dioxide, and each water made an H2O. And your car is very well set up probably. It has a air-fuel ratio sensor and keeps the mixture what they call stoichiometric, so it's just the right amount, not too much fuel, not too much air. And that system's been very optimized. And it's very reliable and relatively inexpensive. And it uses liquid fuel gasoline that's easy to find, has a high energy density, you can refuel in a few minutes. But even that perfect combustion that's been around for a long time emits pollutants. It doesn't just emit CO2 and water. There are other things which are regulated by EPA, which I'll mention in a minute. And even that carbon dioxide, a greenhouse gas, and then the slow abusing of petroleum, which is a finite resource, isn't sustainable. Also, that heat engine has something that's called the thermodynamic Carnot efficiency limitation for heat into work. It's about 50 or 60% is the maximum efficiency for the highest temperature and the lowest temperature in that engine. And in the real world, about half of the Carnot efficiency is reached, so maybe 25 or 30%. So that's not real good, and we'll show you that we can do better. And finally, this system has competition from several types of electric vehicles. I'm going to label that XEV, and I'll explain what that is in a minute. But these use electrochemistry to produce electricity, which is used by a very efficient electric motor and power electronics to move the vehicle. So why must automakers build electric vehicles? Why can't they just keep building internal combustion engines with better control of the air-fuel ratio and better catalysts and better transmissions, et cetera, et cetera? Well, the Environmental Protection Agency, EPA, and the California Air Resources Board can set pollutant emission standards to protect public health. And these are the criteria pollutants: hydrocarbons, carbon monoxide, nitrogen oxides, sulfur dioxide, lead, and particulate matter. And the National Highway Traffic Safety Administration can set mile per gallon standards, corporate average fuel economy. So CO2 then becomes regulated as a greenhouse gas, so that perfect combustion making CO2 is not so perfect after all. And the standards are being very difficult to reach. 54.5 miles per gallon by 2025, that's a NHTSA number. EPA would call, which worries about emissions, would say 163 grams of CO2 per mile. These two things are almost equivalent. Well, the current crop of vehicles, say in 2015, gets about half that mileage and emits about twice that much of carbon dioxide per mile. So it's just getting harder and harder to meet that by improving gasoline engines or improving the ICE gasoline system. And it's impossible for that system to meet the California ZEV standards, which I'll mention and John will get into. So that's why they're moving to electric vehicles. And this is a slide from GM when I was there in the, I think this is maybe about 8 or 10 years old. You can see the director of fuel cell activities used this, and several other executives at GM use a similar slide, where on the x-axis we have the different fuels. We wanted to move away from petroleum. Today about 96% of the energy to move the fleet comes from petroleum, and that's something we have to import, et cetera, et cetera. So we're trying to move to alternative fuels, electricity in a battery vehicle, and even hydrogen in a fuel cell vehicle. So we're displacing petroleum, we're improving fuel economy, and we're reducing emissions. And you can see that at the time GM put the hydrogen fuel cell at the top here, really equal to the battery electric vehicle. So that's the strategy to follow. And it didn't have a single silver bullet. It had all of the above, but ultimately wanted to have more and more of the electric vehicles. Let's talk about some of the different types of electric vehicles in the nomenclature. If X is H, it's a hybrid electric vehicle that has two powertrains, such as an internal combustion engine and an electric motor, and maybe two ways to store energy, such as gasoline and a battery. If it's a plug-in hybrid, that means it probably can put gasoline into the tank, and it can also plug into the wall to recharge the battery. A battery vehicle only has a battery, no internal combustion engine, no gasoline. And if X equals FC, it's a fuel cell electric vehicle, and that uses hydrogen. And all of these systems can help to reduce the environmental impact of vehicles relative to the ICE gasoline system. Some quick examples here. The most common is the Toyota Prius. That's a hybrid that uses gasoline, but also has an electric motor and a small battery. There's a plug-in hybrid such as a Chevy Volt that tries to use mostly the plug-in. Plug it in, drive 50 miles, and then if you need more range, the gasoline engine starts. GM calls it an extended range electric vehicle, but nobody else does. That was GM speak. They did that because they wanted to say the Chevy Volt was a battery electric vehicle with a range extender. I'm not at GM anymore, so I'm going to call it PHEV. The BEV examples are the Nissan Leaf and the Tesla Model S, and these are becoming more common, and they're quite desirable. They're getting very good press, especially Tesla, with the vehicles that have such good performance, and the desire to bring out a less expensive vehicle, which GM also wants to do with something called the Chevy Bolt, not to be confused with the Volt. But anyway, the hybrids and the battery electric vehicles are either very common or becoming common. Now let's talk about the other, the fuel cell electric vehicle. And the one that's been leased in California is the Honda FCX Clarity, and John informed me yesterday it's now called the Clarity. It's a newer version of it. But there's also the Toyota Mirai, which is being sold in California and other places. And Hyundai also has a vehicle, a Tucson, that is a fuel cell electric vehicle. But this is the other. This is in Genesis mode. So a lot of times it's one versus the other. And most people, when they think of electric vehicles, think of the hybrids because there's so many Toyota Priuses around and they work so well. They get over 50 miles per gallon, and they've been improved over and over and over again. Or they think of the BEVs, the Tesla vehicles. And one of the reasons is fuel cell vehicles have consistently missed their introduction date. I know at GM we wanted to start selling them around 2005, 2007, and our stated goal at the time was to be the first, not necessarily the first to sell them, but the first to profitably sell 1 million fuel cell electric vehicles. And it's possible GM will still reach that because they haven't lost interest in it, but they're definitely not the first. And Toyota definitely is leading the pack on this, along with Hyundai and Honda. But things are changing, especially in California, as we'll point out today, and especially John, and Japan and Germany. And the point of it is that automotive technicians in the future will need to be able to maintain and repair these vehicles, which have high voltage, high pressure gas, and a flammable gas. Let's just take a quick look before I go into the technology to see what we're going to be looking at. This part here, the power control unit and the electric motor, are the same as a battery electric vehicle. But what's different is this has a fuel cell stack and a tank that contains hydrogen. I also want to point out, and I'll mention this later, that all fuel cell vehicles have a little power battery, a small power battery, and I'll mention the need for that later. So now let's get into the nitty-gritty of how this works. To understand how fuel cells, and by the way, batteries work, you need to understand something about electrochemistry, oxidation reduction reactions, the anode, the cathode, and the electrolyte, ion flow and current flow in the system, something called the electromotive series of half reactions, the standard potential for those half reactions and how we add them together to get the total potential of the battery or fuel cell, and something called overvoltage, which is an electrical analog of mechanical friction. We always have to pay for friction. Nothing works perfectly. I don't want to go into a lot of chemistry here, but there's kind of a foundation that you need to know about, and if it's confusing, maybe you need to take a chemistry course to learn about. And the first example of the first type of reaction that we're going to talk about is an oxidation reaction. And here's an example. Copper solid goes to copper ions in solution, that's what aqueous means, like water solution, and gives up 2 electrons. And that's an oxidation reaction, when electrons are produced in the half reaction. A reduction is just the opposite of that. That might be copper ions, aqueous in solution, gaining 2 electrons and plating out as solid copper. Notice one is the reverse of the other. This is the electromotive series of half reactions. And all of these half reactions here are written as reductions, so electrons are on the left-hand side. We could reverse it, and then it would be an oxidation, and then we'd reverse this standard potential. Notice they all have different standard potentials, which give the tendency for the reaction to occur. Notice there's one reaction here where hydrogen ions, 2H+, gain electrons to make hydrogen gas. That's going to be pretty important in the following discussion. I'm just going to point out up here there's also an oxygen reaction here, where oxygen and electrons and hydrogen ions go to water. That's going to be important, and that has 1.23 volts. Keep that in mind for a minute. So now, how do we add these together to make a battery? Well, we can take an oxidation reaction, such as zinc being oxidized to zinc ions, and the reduction half reactions, copper ions being reduced to copper solid. We add the two together, and this is the overall reaction. Zinc solid plus copper ions goes to zinc ions plus copper solid, plus electrical energy by adding together these standard potentials, and it comes out 1.1 volt. This is called the Daniell cell. It was invented in the 1800s, and it's an early battery. It's a good illustration of how electrochemistry can make electricity. And by the way, this is DC electricity. This, I think, is real good way to understand this because it's so picturesque. Let's start in this right-hand beaker here. Here, the zinc is going into solution to form zinc ions, and this is a water solution called aqueous, and it's giving up electrons when it does that. So it's an oxidation reaction. Those electrons make that zinc electrode, the anode, make it negative. The place where oxidation occurs, electrochemists always call the anode. Those electrons are flowing over here to the copper, where copper ions meet those electrons and plate out as copper. Copper ions plus electrons form copper solid in that beaker. Notice electrons are flowing in these external wires, where ions are flowing between the two beakers in the solution. Electrons don't flow in solution, and ions don't flow through the wire. So this is the Daniell cell. This is an early battery, and it illustrates how the battery works and how we name the anode, the cathode, the negative electrode, and the positive electrode. So this battery, if it was hooked to a load, like a light bulb, could produce electricity and light the light bulb, but it would slowly run down and be discharged. And then if we wanted to charge it back up, we could hook a power supply here, reverse these reactions, and go back to the initial state and use it again and cycle discharge, charge. And that's how a battery would work. Fuel cell is a little bit different, still uses electrochemistry. Again, let's start over here on what's happening at the anode. Hydrogen gas is coming into these channels. It's diffusing through this diffusion media, which I'll explain in just a second, getting over to this catalyst where it splits into hydrogen ions, H+, and the electrons, which go back to the electrode, flow over here through the external circuit, come back over to the cathode, and can combine with those hydrogen ions, shown here, the oxygen, which is coming through this channel, and those electrons to form water. So in this case, ions are flowing through this electrolyte, which is a very special electrolyte this time. It's not an aqueous solution of water. It's actually a solid piece of plastic that is permeable to hydrogen ions. And I'll point that out a little better in just a minute. So unlike the battery where it discharges, as long as we keep supplying hydrogen to this side and oxygen or air to this side, because air contains about 20% oxygen and works just fine in a fuel cell, this will keep producing current. And that current can be used to run an electric motor or do something, as I'll show in a minute. Of course, you don't use one cell. Just like a high voltage battery, you put many cells in series to form the high voltage. This shows the components in a little bit different schematic, and it identifies something called the membrane electrode assembly, which is the gas diffusion layer, the catalyst, the membrane in the middle, the other catalyst, and the other gas diffusion layer. And it tells you that the membrane electrode assembly, the catalyst, is platinum on high surface area carbon. A catalyst is something that speeds up a reaction that might normally be slow. So the reaction is spontaneous and will happen, but it doesn't happen fast enough because we're impatient. So we find a catalyst that makes it happen fast. The gas diffusion layer is conducting because it has carbon coated on fibers of Teflon and lots of little channels in here so that the hydrogen is broken up into streams and meets the catalyst where it can react. This is a picture of a fuel cell stack. It's called a stack because many of these are put in series, anode to cathode, just like you'd put batteries in a flashlight, plus to minus, in series to build up the voltage. I want to say something about this polymer electrolyte membrane. Some people say PEM means polymer electrolyte membrane, but I'm saying it means proton exchange membrane. In other words, it conducts protons. It's a very acidic membrane. As I said, it's plastic, but has these fluorine, which are very electronegative functional groups, as well as these sulfonic acid groups here, SO3, and it absorbs water, and then it conducts protons. So it's a really interesting membrane that is very different than a normal electrolyte that we think of as a liquid. By the way, the electrolyte in lithium-ion batteries isn't a liquid either. It's oftentimes a lithium phosphate compound. It's a non-aqueous, non-water type electrolyte, and that's certainly what this is. And by the way, this is a solid. So let's look at the chemistry and break it down. The oxidation reaction is shown here, and that has 0 volts from that electromotive table. The reduction is shown here. Remember I said it had 1.23 volts. We add the two together to get the total voltage in the total reaction. We're taking hydrogen and oxidizing it to water. You know, you can burn hydrogen in air and to make H2O, but then you've got a heat engine, and you don't get all the energy out of it like you do with this electrochemistry. Unfortunately, the fuel cell has some loss mechanisms, so we don't get this whole 1.23 volts, and I'll show an example of that in just a minute. We get a little bit over half of that, so the efficiency is maybe 50 or 60%. And that's not as good as lithium-ion batteries that can be 80 or 90% for the energy out versus the energy in. They don't have quite as bad of a sluggish reaction at the reduction portion of the system. This shows what happens when we actually take a fuel cell and actually make it do work, make it produce electricity. At open circuit, remember, it's about 1.23 volts. Engineers want to have a fuel cell produce about 1 amp per centimeter squared. And at that electricity production level, remember this is DC electricity, batteries and fuel cells make DC electricity, we're losing about half that voltage. We're only about 0.68 volts here, a little bit over half of the voltage. Most of the loss is at the oxygen electrode. It's that sluggish reaction that doesn't want to go as fast as we want it to go. We want to draw current from the system, and it says, hold on, wait a minute. And we say, no, then we're going to still go fast and just lose this energy. Some small amount is due to resistance to ion flow through that plastic membrane, and a little bit is due to a concentration gradient that always happens on an electrode. There's a depletion right at the surface of the electrode. But we're losing most of it at that oxygen electrode. Unfortunately, electrochemists have been studying that electrode for a long time, 50 years or more, and still haven't come up with a better electrode that can reduce that overvoltage. Let's talk a little bit about hydrogen storage, because that's really brings in another safety aspect here and something we have to deal with. The hydrogen is stored as a gas at very high pressure. Hydrogen is very hard to liquefy, so it's stored as a gas at high pressure, 10,000 pounds. And that's the pressure. I mean, if you want to put this in perspective, if you went down 22,500 feet in the ocean, that would be the pressure, extremely high. People who use the metric system would call that 700 bar or 70 megapascals. By the way, a unit of 1 bar of pressure is about 1 atmosphere to us, about 14.7 pounds. And that's delivered at low pressure to the fuel cell. It doesn't need that high pressure. That's just for storing it and squeezing it all into this tank, which I'll show in a minute, what the tank looks like. Also, the hydrogen has to be very pure, and especially it can't contain things like carbon monoxide. That would poison the catalyst. Air can be used as a source of oxygen in a fuel cell, and it's also supplied to the fuel cell at low pressure typically. And then the water vapor, pardon me, that's produced is conducted away through an exhaust pipe. By the way, if the Army was using this in a desert, they could collect that water and drink it. That's how pure it is. So the components include the fuel cell stack, which are hundreds of cells in series to get a high voltage, about as high as a battery electric vehicle, 300-400 volts. The storage tank at very high pressure, an electric motor and power inverter, just like the BEV. Why do we need a power inverter? Well, the electric motor in all electric vehicles is an AC motor, so we have to have something that takes the DC to AC. And when we stop an electric vehicle, we want to let the motor become a drag on the vehicle and turn into an alternator, put that electricity right back in the battery. So it has to make the AC from that alternator into DC, so it's a bidirectional inverter. And then finally, the power battery. A fuel cell electric vehicle is automatically a hybrid because it needs that little power battery so that it can collect the energy from regenerative braking. Also needs it for the takeoff. Rather than have the fuel cell try to produce all that electricity, it's good to have a power battery do that. So again, let's go back to the picture. The power control unit, which is the thing that makes DC into AC and AC into DC for the electric motor from the DC source, the fuel cell, or the battery. And then, as I said, these are always AC motors these days. They're more efficient. They're about sometimes 90% efficient or more, and that's why these AC synchronous permanent magnet motors are used in electric and fuel cell vehicles. The stack, as I mentioned, this little tiny high output battery to collect regen braking and to give some power for takeoff. And then this tank that has the high pressure hydrogen. Let's take a look at the tank. The tank has an inner liner to prevent hydrogen from permeating out, because hydrogen is a very small molecule, the smallest of all. And then it has some structural members, a carbon fiber and a glass fiber plastic layer, so it can contain that 700 bar hydrogen. This is the tank in the Toyota Mirai. It has about 5 kilograms of hydrogen in it. That's not very much weight of hydrogen. It turns out that 5 kilograms of hydrogen have about the same chemical energy as 5 gallons of gasoline. But since a fuel cell is about twice as efficient as a gasoline engine, that's equivalent to 10 gallons of gasoline, which can easily take the vehicle 200 to 300 miles. Here's a slide from my GM days where we're very high on fuel cells. No emissions other than water vapor, which is not considered important. So this is a ZEV. Doesn't use any petroleum. The hydrogen doesn't come from petroleum. I'll talk about that in a minute. It's more than twice as efficient as the ICE gasoline. Comparable precious metal, platinum content to a catalytic converter. Can go just as far, 300 miles. Can refuel fast. 60% fewer parts, 90% fewer moving parts, can operate in cold and hot climates, can make a family-sized vehicle, and it has a synergy with renewable resources. I'll come back to that. That's a very important point. Let's talk a little bit more about hydrogen. Hydrogen is not a fuel. We don't put a well in the ground and find hydrogen, so it has to be produced from something. Right now we use natural gas, which has a lot of methane. Natural gas is mostly methane, so the hydrogen in the natural gas becomes hydrogen. And it uses steam reforming, so two waters are actually converted into hydrogen during the steam reforming process. But the diversity of the sources are one of the strengths of a fuel cell vehicle, of the hydrogen from a fuel cell vehicle, because it doesn't come from petroleum, coal, we can electrolyze water, we can use biological, but even those are still not sustainable. Let's look at some sustainable ways to make hydrogen. And I thank my friend at National Renewable Energy Lab for this, who is very good co-worker of ours at General Motors and helped us get up to speed on a lot of these things. He starts with solar energy. Solar energy can make heat in a concentrator that can break water apart because it's so hot. It can drive a windmill that makes electricity that electrolyzes water into hydrogen and oxygen, and we store the hydrogen. It can shine on photovoltaic panels. Now, I have more to say about that in a minute. They make electricity that can electrolyze water. It can make biomass, which we can convert to hydrogen. It can make special bacteria. It can use special bacteria that break water apart, photolyze it, and make hydrogen. Or it can use photoelectrochemistry, which John Turner is the real world expert in, to actually split water in little tiny electrodes that he studied, but in a bigger system. So it's a direct process, unlike this two-step process using PV panels and an electrolyzer. So let's look at a system that we actually made at GM in, I don't know, about 2005, I think, 2007. We had solar panels back here collecting solar energy. They were photovoltaic panels. We had an electrolyzer that split water. We fed water into it. It split water into hydrogen and oxygen using electricity from the solar panels. The hydrogen was stored in a tank and dispensed at high pressure into this fuel cell vehicle, and this is from Project Driveway. This was a test fleet that GM had. And we fueled this vehicle with hydrogen from the system. So when you get in this vehicle and drive away, and I use this kind of in my class to ask students, where did the energy come from? Trace it back to its source. Well, the energy to drive this vehicle came from sunlight, so you're really driving on sunlight. And I'll mention that one more time in connection with another project on this slide. And this shows the United States, and even California isn't the center of the universe on this. There are other people that are interested in this, other countries. Germany, for example, is very interested in solar energy, and as is Spain. Germany set a record on June 6, 2014. Half of the electricity was produced by solar energy. Germany has built a solar to wind project, so that's similar to our wind to hydrogen project. I'm back to John Turner and solar energy doing everything, making even the wind, and which it does. But anyway, they use wind energy to split water to make hydrogen, and then use that hydrogen to fuel a vehicle, similar to the way we use solar energy directly to do it. And finally, Japan is using wind power to produce hydrogen and wants to have that running by the time the 2020 Olympics, the ones that just ended in 2016, they mentioned the Tokyo. Well, I had that in my slide here. And it's going to be near the reactor that was ruined and by the tsunami. So that's kind of symbolic. And also, South Korea has opened the largest fuel cell plant in 2014. So there's other people that are supporting this. Let's take a look at what this can mean. And this is from California, from the Air Resources Board. They're showing here how there's different aspects of where greenhouse gas emissions can come from in a vehicle. Some of it comes from making the fuel. Some of it comes from the fuel being used by the vehicle. And when we say a battery electric vehicle has zero tailpipe emissions, that doesn't mean it has zero emissions overall, because the electricity to charge the battery came from somewhere. And if it came from a coal-burning power plant or a power plant that used fossil fuels, there was some greenhouse gases produced, as well as some air pollution. But they show how improving the system here, improving the gasoline engine, will reduce those greenhouse gas emissions from this high number here, maybe over 500, where maybe 380 of it come from the fuel exhaust pipe, down to maybe something over 300. And hybrids can get it down further. But notice the fuel cell vehicles have no greenhouse gas emissions from the exhaust pipe. They do have some from the electricity generation or from the hydrogen production, but they're very, very low compared to these other vehicles. So this is how California wants to reduce greenhouse gases, as well as, I'm not showing nitrogen oxide, sulfur dioxide, smog, ozone. All those will be reduced by these vehicles, because these two vehicles here are ZEVs. They're zero-emission vehicles at the tailpipe. Now, this kind of shows here how a fuel cell vehicle may be the small child today, or the genesis today, but using this chart, which is a projection from California, you can see that it's the big dog here over in 2050. It's over half of the fleet they want to have fuel cell vehicles in order to meet their air pollution and greenhouse gas reduction standards. So that's very interesting, and I think John will get into that a little bit and show some things that are going on with something called AB32, which is where this came from. So why are some people so critical of fuel cell electric vehicles? Well, they love battery vehicles, and they're great too. And there is an inefficiency here if you only look at one aspect, that is making the hydrogen using electricity, which is made at power plants, because there's only a 60% efficiency in electrolysis and another 50 or 60% in the fuel cell, so you're still losing a lot of energy. You also need a fueling infrastructure, and who wants to step up and do that? Well, we'll show that in a minute. These criticisms are not showstoppers, because, as I've shown, hydrogen can be made in efficient ways that use diverse sources, and California, Japan, and Germany are committed to that, to a fueling infrastructure. So let's look at a few aspects of this. The fuel cell needs a new infrastructure. Battery looks great on that. It has home charging and expanded fast charges coming. Fuel cells win this one. They're a fast fill and can be driven across the country. They can replace heavy vehicles. This one is still to be determined, although Tesla's doing a great job with their superchargers. 30 minutes to charge a vehicle to go 170 miles. That's getting pretty good. And both these vehicles are being researched and improved as we speak. There may be a better way to store hydrogen than high pressure, and batteries should become lighter. And I'm going to call this the power of and, that they both have a place in an advanced powertrain portfolio. So in summary, the vehicles are here, all these different types. The batteries and fuel cells use electrochemistry, so you need to learn something about chemistry, oxidation reduction, which we call redox reactions, rather than combustion, because that gives higher efficiency. Government regulations are driving this, the greenhouse gas reduction, petroleum reduction, and the ZEV mandate. And both these vehicles have some advantages and limitations, and rather than worry about the limitations, let's work on them and improve them, because they're both going to improve the impact of vehicles on reduce the impact of vehicles on the planet, and contribute to a more sustainable transportation system. And this is the power of and. They could satisfy different groups of customers. And finally, renewable energy. The synergy of renewable energy in these electric vehicles, and maybe even synergy with connected automated vehicles, is a very strong point. So now let me just give you some resources for further use. The Department of Energy has an excellent site that explains these technologies and the different types of fuel cells, and they have a annual meeting where they talk about producing hydrogen and work on fuel cells and all the aspects of this. And the alternative fuel site, this is going to tell you about hydrogen, natural gas, biofuels, ethanol. That's a very good site. Of course, the California sites, the ARB, John will mention this in a minute, and a fuel cell partnership. And the Northeast states are joining California in their, at least in their ideals, and they have some good things going on and should be looked at. And finally, a shout out to our own site here at CAAT. We have a technology site, and I'm going to summarize this with one slide, but we have I would call it solid gold website that has a lot of information on it. And one of them is the technologies, and of course, automated connected vehicles are the hottest topic right now. But we also have a fuel cell as one of our technologies. You can see them on the side here. So you click on this top tab when you go to www.autocat.org. And I'm going to be updating this with some new information that I learned in putting this webinar together, as well as linking back to John. As you'll see, he's really up to date on this and kind of leading the way on training technicians in this field. So don't forget to sign up for our newsletter, and don't forget to look at our resources, which this webinar will be listed in our resources. And the other thing I'd say about our resources is we have something called seed funding, where we have funded experts, subject matter experts, to compile and put together total curricula, syllabus, learning lectures, and we have that out there for free on topics like electric vehicles, automated connected vehicles, lightweighting, etc. So in summary, visit our website, sign up for our newsletter, take a look at our seed funding here, and finally, join us at NACAT. We're actually hosting this annual meeting next year in July, the North American Council of Teachers annual meeting, and John and I think his coworker Ken Mays will be there, and we'll be talking more about their efforts to certify technicians. And John will get into that, and I think it's time for me to say thank you. And I don't know, Mike, do you want to have some questions now, or would you rather wait till John goes through his presentation?
Nelson, I would like to pause for a moment. There's several questions that have come in by email I'd like to forward to you. I like your quote here from Einstein, by the way. I think you just answered this one, but the question that came in by email, did he say the curricula are free? Is there some catch there, Nelson, or is it really the fact that it's fun?
The only catch is you come to our site and download it. No, we have, I would say, 12 completed seed funding partners. If you look at our site, you can see them all listed, from Lawrence Tech, Utica Community Schools, even we have some high school courses in science. And most recently, we have 2 courses being prepared on connected automated vehicles and 3 on lightweighting, 2 of which are complete, which are done by Kettering. So yes, these are actually free, and that's part of our ATE, I guess you could say, initiative to actually, and you can apply for seed funding if you have an idea for some, like for example, if somebody wanted to put a course together on fuel cell electric vehicles right now, and have a curricula where they'd have a syllabus, lectures, etc. We would consider that. Although right now we're kind of at the end of our funding period, but we hope to go forward with this in a new funding period, and we'd start all over again with being able to fund this. But that's what the seed funding is.
Well, thank you.
So that site, let me go back to it and show that site explicitly. This site right here.
Right. Good.
I'll point to it if I can.
Attendees will
I think I lost my arrow. There it is.
The attendees will get the slides, so they'll be able to go right into them to find these links. They don't have to write them down. So
right.
Good. Nelson, another couple more questions. What's the service life anticipated for these sort of things? If it's 100 hours, is it 10 million hours? What would you guess?
Well, Toyota is selling the vehicle, the Mirai. John may be able to answer that better than me, but I think it's going to be comparable to a vehicle that's on the road right now. They're not leasing it, just leasing it. When they just lease it, that means there might be some fear that some component or something might not have a long service life. But I know the same question gets asked, or got asked when Chevy brought out the Chevy Volt. How long will this battery last? Or the Prius, how long will that nickel metal hydride battery last? So you don't really know the final answer till you actually put the vehicle out there. But my guess is they're testing, their internal house testing, and they try to do this in a short time and then predict 10 years out. It's probably going to last as long as a current internal combustion engine gasoline vehicle.
John, would you like to comment on that?
Yes, some of the research I've seen already coming out of Honda the fuel quality is really what's going to matter the life of this thing. If you have no contamination and your fuel is at 99.9% good quality, you do not lose any cell structure space to produce electricity. So the contaminants, that seems to be what's limiting the life of these right now, is getting, I usually say inferior fuel, but fuel that's maybe not as good quality as they want.
Okay.
So ASTM and a couple of the other outside agencies are doing a lot of testing on that fuel quality right now to set standards for these stations.
Good. One more question for that's come into the chat window. You know, hydrogen, of course, is a fuel, an explosive fuel. Have there been scenarios developed for a collision event that could result in a serious issue associated with the hydrogen?
I can take that one, Nelson.
Sure.
Go ahead, John.
One of my assignments here at the college is I provide first responder training throughout the state of California. Around 400 firefighters so far we've trained on first responder, and that question comes up quite often. The answer to that is much like natural gas. A natural gas vehicle that is storing natural gas compressed at 3,600 pounds, when it vents to the atmosphere, rises at about 300 feet per second, whereas hydrogen, because of its structure and its chemical makeup, rises at about 600 feet per second. So even if it was to vent off in a collision that would break that tank, which would take quite an impact, the fuel would be vented into the atmosphere and dispersed before you would have some type of flash or fire or anything like that. So there has been a lot of safety put into this type of fuel because of the structure of the fuel.
That's a good response, John. Thank you. One more, Nelson, for you. What's the refuel time? I pull up into a station, assuming I could find one. That's sort of a joke, but I know the infrastructure is coming along. I pull up into the refuel station. How long am I going to be there?
Well, I think Charles was a little bit, Charles Freeze was a little bit, I'm going back to that slide because it's actually on there, where he says 3 minutes. I would say closer to 5 minutes. It's about the same as it is, and I've done this. I fueled these vehicles with the 700 bar hydrogen, and it's pretty uneventful. I mean, it's just, the only thing that's different is you put, depending on the station, that we had two of them at GM, one that didn't communicate with the car and one that did. But either one, you pull down a handle and it kind of locks in, and then, 5 minutes later, it's full.
It's 5 to 8 minutes right now in California.
Okay. Well, that's not bad. It's better than me charging up my Tesla, which doesn't take too long.
Yes.
I didn't mean to imply I had a Tesla. I wish I had a Tesla. That's another story. Take us back, Nelson, to the question frame there. Colleagues, thank you for your questions. Keep them coming in either by email or by the chat window. We appreciate that. Let me move one ahead and let's enter part 2 and invite John Prilla from Rio Hondo to come on. John, the floor is yours. Go ahead.
Thank you very much. So I'm going to talk about what's happening with the technicians and what's happening with the movement in California. California has mandated a zero emissions policy that's being reinforced to fleets and transit agencies, and now to consumers for something. Even now we're down looking at lawnmowers and yard equipment, things like that. We've got to now move away from diesel, particulates, and fuels. So their mandates in 2025, they're very strict, and California has always led the way with emissions and what they will allow. So the governor has come up with a couple of policies, and one of them was AB 8, which really started the ball rolling on the hydrogen side. But we have a couple of other policies out there, AB 32 and a couple before that. The California Energy Commission came along and said, you know what, we're going to make this thing happen, and we're going to make this happen correctly. So they put together a committee in California called the GoBiz, which was Governor Brown's think tank. I am the education person on that think tank of about 60 people. And these are people from government agencies, fueling companies, auto manufacturers, California Fuel Cell Partnership, the Center for Transportation and the Environment, CTE, which is very heavy into this. So we all come together as a think tank to start putting ideas together so we can standardize the fuel stations, get the infrastructure in place, and get education out there so we have technicians to run the stations, service the stations, and also work and manufacture on these vehicles. So AB8 came out in California in 2014, and what it mandated was $20 million annually allowed, set aside starting April of 2014, that California would put into the infrastructure. So that funded the first 59 stations to be put in place. The unique thing about this is, we'll talk about this when I get into some of the other slides here, is that is not gone away. The funding is what they would call from here out thereafter. And on top of that, we've had funding from the Federal Transit Association. So not just California is benefiting from this. We have 13 transit agencies in 13 different states who shared $55 million the first of this month to put these infrastructures in place now to put transit buses with zero emissions, where they could be electric or hydrogen. And this pays for the infrastructure, battery charging or hydrogen, plus some of the training which we're developing here on our campus. So one of the programs we originally had here was compressed natural gas, liquid natural gas, and propane. That is an associate's degree, a 2-year associate's degree I have here that transfers to Cal State LA engineering program, so that they can the students can go into an engineering program and then move into manufacturers, helping to design and test and keep the technology going. So our campus, being in California, is very centrally located to a lot of the manufacturers and the testing facilities. So we put together a new associate's degree, and this is what our NSF grant was that was funded last year, to put an associate's degree together for electric cars and fuel cell technology. So in California right now, I'm going to expand on that list that Nelson had up there earlier, that we now have all these manufacturers with vehicles here in the States. Mercedes has had a test car out, the B-Class, which I've driven for a while. Audi just brought out their H-Tron Quattro. Chevy has a fuel cell EV, which is Equinox right now. Honda Clarity has been out for quite a while, but Honda's had 8 generations before that with a Honda FCX. So Honda's had a lot of time and a lot of money invested in this project. Hyundai has the Tucson fuel cell, and they are coming out with a sedan here fairly quick. Nissan has X-Trail, and then Toyota has a Mirai, and rumor has it we're going to be seeing either a 4Runner or something like that come back with the fuel cell in it also. And so you'll see right now, these are the vehicles that are available right now. You can buy them, you can lease them, and they are selling here pretty quick. So some of the manufacturers are actually got small fueling stations on top of their property. So this is what I was talking about a little bit earlier. We've gone up to 19 different transit agencies totally off that money. The oldest out here that's had this technology is Sunline Transit. They're located in Palm Springs area. They've been running fuel cell buses for about the past 8 years. And this is one of my partners out here. I am partnered with them in developing curriculum and putting together some of the safety training that's going to go into the other agencies. AC Transit's around San Francisco. They have their own fueling infrastructure, and they're using an experimental system to compress their hydrogen, which is using a hydraulic system, not a conventional compressor system. So if you go to their website, they have pictures and animation of that new type of compression, which seems to be working very well. Orange County Transit just got their very first fuel cell bus last month. So even the local guys here around me are getting on this. The other people that are using this stuff, Class 8 vehicles now, drayage trucks. California ports of Los Angeles and Long Beach have very strict laws on the ports. You cannot take a diesel truck on the port. It has to be something of alternative energy, which would be compressed natural gas. Liquid natural gas seems to be a real favorite. And they are starting to run a hybrid system out there that BAE is making for some of the different truck manufacturers. U.S. Hybrids, which is located right here in Torrance, they do a lot of military and special projects, and they're doing shuttle buses now for the airports. So they started building the UPS, which UPS is now had a couple of experimentals out there. So even the people who have this as a daily means of delivering packages and things like that, they're looking at the possibilities and what kind of costs are involved and
they're giving us a lot of data back about how long these things are going to last. Where my group comes into this now, California AB 8. We've set the money aside, and it's every year thereafter. So this is not a grandfathering grant. We have allocated $20 million annually, started December 2015. This is for infrastructure, product, and education. So California now says we need education to make sure this happens correctly. We have 59 stations that are in place or will be in place by the end of this year. The goal is to have at least 100 publicly available stations in California by the end of 2018. So this is California Fuel Cell Partnership. They are partners with just about everybody. They're running a very active map. So some of them, like Toyota Mirai right now, they have this map active in their vehicles. You punch up the dashboard, it'll tell you where the vehicle's fueling station is close to you where it's at, and if you're capable of making it there with the amount of fuel that you'll have in the vehicle at the time. So this GPS, this automation stuff is actually already in the vehicles, and it's happening right now. So this brings me back to my students. A typical automotive student is in the field known as a gearhead. They like internal combustion motors. They like to race them and play with them and modify them and things like that. The typical technician that's going into this type of technology that we're talking now, electric cars, hybrids, fuel cells, they're a whole different group. They're very green energy minded, they're environmentally minded, and they want to make a statement by what they're working on and what they're producing and how they're going to make the air cleaner in California. So this student now has got to go back and look at STEM type sciences, which would be my science, technology, and the engineering side and math. A lot of physics, a lot of chemistry, and a lot of math go into my classes. We've got students that have to have mechanical skills that a normal mechanic would have, but now I have to have electronic skills. And notice I did not say electrical skills. I'm talking about electronic, which Nelson had touched on earlier. We are looking at high voltage electronics that are switching voltages from very high voltages to very low voltages and recapturing voltages in lost energy in braking and cruising to put them back into the battery packs. So there's a lot of conversions, a lot of very expensive electronic pieces in there. My students also have to understand the software skills now to read the computers, to go in there and to basically look at the onboard computer system. A Toyota Prius right now has 17 to 19 computers on it. So my students have to be able to go in that software, determine which computer system has got a malfunction, and correctly identify what the problem was. It might not be a computer, it might be something else that's causing the error or causing the malfunction. So the students have got to get better skills for what they normally would to be an automotive mechanic. So this brings up to the other side of why this degree came about. We are losing cars with oil changes at 3,000 miles. As most of you know, the vehicles that you drive day to day, the oil changes are now using very high synthetic oils, manufactured oils. Oil qualities have changed quite a bit, and you don't have to have an oil change every 3,000 miles. You're going 7,500, 10,000 miles. Some of them are going as high as 18,000 miles. Well, on a hybrid, the engine shuts off sometimes as much as 60% of the life of that engine, so it's extended the life of that engine. So that means now my technicians don't have to look at replacing brakes. Brakes are going 150,000, 200,000. I've seen them as high as 320,000 miles on a hybrid. On an electric car right now, we've got an electric car that has 99,000 miles on it and still has the factory original brakes on it. So my students are not looking at doing maintenance, they're looking at doing more of high voltage corrections, looking at batteries, syncing batteries, and making sure the systems are operating correctly. But they've also got to look at basic automotive skills for the braking systems and things like that. What's changed on the cars is we no longer have drive belts to drive these accessories. All the drive accessories now have gone to electronics. They're on CAN protocols, much like your phone talks on. So we're talking on communication networks that are very extremely fast, and so they've got to learn new skills with the different types of vehicles, some of them that don't have manuals yet. Some of them, my students are actually manufacturing or creating the manuals that we share with the manufacturers. And that stuff will be posted on ATE probably by the end of next year from us, much like what Nelson's doing with his curricula. So embedded systems that are in the cars, lab testing, all that stuff. This is a whole new mechanic that has to be put out there. So when my degree first got put together as a brainstorm, we went to ONET, who does all the job classifications in the States. And ONET came up with this basically and said, well, isn't that just an auto mechanic? And we had to go back and re-educate them. Same thing with the California Employment Development Agency. There was no job classifications for a fuel cell technician or electric vehicle technician in existence. So we created this with the help of them and much of the people on the think tank team and came up with a job description. And this is what ONET is basically posted on their skill level. So you can see assembling fuel stacks according to the mechanical, electrical assembly, building fuel cell prototypes, following engineering specifications. So now a typical mechanic has to have engineering skills. So these guys are not the guy that's going to go out there and make $12 an hour. They're going to be well educated and be making quite a bit more money. Job sources right now that are out there, we have seen ONET's skills are saying somewhere in the area of 12,000 nationally. California is looking for somewhere in the area of 7,000 within the state within the next 5 years. So we have a lot of jobs out here for guys that have these skills. So as we go back and talk to the manufacturers, they're wanting better education. So the manufacturer on this particular product, which happens to be a 1989 Honda Insight, one of the very first hybrids out there, if you're looking at that picture, it doesn't look like a whole lot. It looks like a couple boxes and some orange wires. Well, those wires are 225 volts. There's a DC-DC converter that converts the voltage from the charging side to the vehicle. You have an inverter, which we talked about earlier, that converts high voltage to low voltage and then puts it into the battery pack. So if I have a technician that is only able to work in this, it's certified in the skills area, what is a certified technician? And that's a question we haven't been able to answer yet. This is such an emerging technology. The skill sets are being developed as we talk, and I'm heavily involved in those negotiations right now with a couple of the certifying entities. We've had some discussions with SAE, which were on the committees, ASE, which now has an L3 certification for hybrid and electric vehicles, but not fuel cells yet. We've already had some talks with and discussions with them. So this is very typical of what my current tech is looking at a vehicle. Much like what Nelson was showing earlier in the car, this is kind of a breakdown. This is a Mirai, and you'll notice a couple of things on this that are different than what you would see on a normal passenger car. Yes, I have an electronic engine up here. I have an electronic controller that controls that engine, but I still have a mechanical braking system. I have a fuel cell stack right here that it does all the fuel cell exchange to electricity, high pressure piping at 10,000 psi, 2 different fuel tanks which require fuel tank certification, which is being developed right now, and a standard battery. This would be the almost identical battery that would be in a Camry. So this is metal nickel hydride. So I have a 12-volt operating system for the accessories in the cars, yet I have a high voltage system. So I have basically 4 different propulsion systems on the same vehicle that technician now has to understand, whereas before they had a gasoline internal combustion engine and all they had to know was that. So the technicians have to know these things. So these are some pictures of my students in the labs actually working on these things. And what's hands-on, high voltage, this happens to be a compressor out of a Prius, which is 201 volts up to 223 volts. Remember, we no longer have a drive belt moving that air compressor. We're doing it with electronics. Now it takes a special fluid to go in it because it can't be conductive to electronics. Otherwise, the compressor will catch on fire or explode if you've got the wrong chemicals in it. So the students are hand trained on the physical piece. They take it apart, they put it together, and then we go out and test it. So currently right now, I have the only fuel cell technician program in the state of California. 23 students currently enrolled in this, and about half of them are going to be graduating this May. They're that advanced. They are working in the industry. They're preparing to go into it. This is actually a technician that works for Penske Motors at a Toyota store. He comes to our campus because he can get his further information from us that you cannot get from the factory, because their factory gives them down to components and we give them down to the systems. So they're being able to help us develop this curriculum that we'll be sharing also. The other piece is for the big transit buses. These high pressure systems that go out on their air conditioning compressors are 248 volts. Your car that you're driving has electric power assist now. It could be 45 volts to 85 volts. So if a technician does not know this, he could get killed or get really hurt pretty bad. Electrical burns, things like that. So we're bringing the students up to the current technology as fast as we can, and these guys get jobs as fast as they start going through this. This is one of our fuel providers that's here in California, Stratus Fuels. These are one of the companies here that are building the stations. These two gentlemen right here actually are the president, vice president of the fueling. They drive these Hyundais, bring them up to the students. We get to take them apart, look at them, look at the systems. This is my first graduating group right here of students that will be graduating in May. So from that seed money that California started of $200 million and putting the $20 million thereafter, we've been able to develop a complete program, get the students knowledge, get them a certificate, get them an associate's degree that's transferable into our bachelor's program, and get them into either a master's program or get them into the industry working. This has been a great partnership with California. They've been able to come back, and we've been able to take what we've developed with them. We are sharing this with Central Oregon now. Ken Mays and myself are doing a joint project here. And these are the people we're talking with, trying to figure out who's going to do the certification for these technicians. Because coming with the new technology, we need to have these guys have that technology to take out with them to be safe to work on the vehicle, but we want the consumers also to be safe. Besides working on the vehicles, we're working on stationary power supply, which would be fuel cells that are replacing the generators. So this is something we just moved into with solid oxide fuel cells. We're currently building our lab right now with a $200 grant or $200,000 grant that the state of California has put out for the existing programs. We'll be getting that probably in January, and we will be building a solid oxide fuel cell lab here so we can now move students out of transportation to home energy and backup generation too. And with that, I'll leave that open for questions also for anyone that has anything on the education side.
Thank you very much, John. Here's one of the questions that came in the chat window. How can you fit all of that stuff, all that STEM stuff, into a two-year program? Can you do that? Or is it really more than a two-year degree program?
We have a two-year degree program, and my full-time students are going through this curriculum in 2 years. If they're doing part-time, it takes them about a 3.5 year.
Sure.
But the first initial group actually are on track to graduate in 2 years to do this. They're here 4 days a week. I run night classes and daytime classes, so I can split the technology up to 2 different groups. We have the engineering guys that are here during the day, and we have the guys from the industry that are coming back to improve their skills coming in at night. So we're off in daytime and nighttime just for their convenience.
That sounds good. So it's possible to do this within the scope of a two-year degree program.
Absolutely.
Related question, you touched on this, is certifications. All automotive technicians, there's a strong certification, AS, EE type of certified people. Is there an industry recognized certification yet for a fuel cell vehicle technician?
Not at this time. We are working on that project as you speak. We're trying to get the people together that normally do these certifications, because it's such an emerging technology. It hasn't hit all 50 states yet. They're lacking behind in that certification. Myself, Stark State, and a little bit Macomb and Wayne State, we seem to be the ones right now that are pushing this. Stark States in Ohio, they have been doing fuel cells at their program, but they're actually getting some fueling or buses here in the near future. We're talking like in December. So I've actually had discussions with the Fuel Cell Coalition there about using some of my curriculum with their curriculum to try to get their technicians in that state up to speed. So we've been able to share a lot of this education and curriculum that we've already developed with the states that are getting these fueling infrastructures in place.
You know, a question came in from the chat window, and I think it makes a lot of sense. This is a great application of STEM technology, right? From everything from the physical chemistry of the electrochemical reactions onto the electronics that you've mentioned. You know, the question is, you know, these materials and slides, we should be able to incorporate them in some of our STEM classes, even if we're not directly automotive technology instructors, wouldn't you think?
That is correct. That's what brought about the change of us not just doing automotive transportation, but doing stationary fuel cell backup power generators. Again, California being the emission laws that we have, diesel backup generators have to be gone fairly soon in the state, and we have to replace them with a sustainable energy. Right now, it looks like a fuel cell is going to be that energy.
Now let's respond to a comment in the chat window that, you know, the market penetration for these type of devices is modest, as you know now, and there may be a lag in demand for these technicians. On the other hand, I see this as a sort of a triple market, right? There's automotive and there's mass transit, and then there's power generation technicians working on fuel cells. How would you envision, you know, how would you fractionate that market? What fraction might go to automotive, and then what fraction to mass transit, and what to power generation, if you had to guess?
Well, there's also one that we hadn't mentioned, which is spacecraft. We have SpaceX out here, and SpaceX is actually hiring some of my guys because they understand high pressure piping and things like that. So
Sure.
they're not just limited to that area. The students here can move into other areas, aircraft industry, transportation industry, or power generation. Right now, I'm probably looking, if I had to guess numbers, I would say about 30% of them would be in the transportation side. I would say 30% of them would be in the transit side or
Yes.
fleet. You're probably looking somewhere in the area of maybe 20% of them going into stationary as an auxiliary piece to another skill they've got with CNG and LNG.
Yeah.
And the remainder is probably going to be somebody who's going to go into mechanical engineering that would go to the manufacturers and be one of the design people or something like that.
That sounds about
So
right.
we're able to place all these guys in their areas of interest.
Okay, fascinating. Let me turn back, if I can, to a question to Nelson. Nelson, a question came in by email, and it says it looks to this person like for short-range trips, it's going to be the battery electric vehicles, and maybe for long-range trips, the fuel cell electric vehicles might be the solution. Would you like to comment on that, Nelson? Does it make sense to you?
Yes, it made sense to me, and I actually had a slide in here from that same presentation by the GM executive that was given to the Department of Energy, where he showed a diagram showing battery electric vehicles only for city.
Yeah.
Elon Musk has shown that that's not true. His supercharger system can charge a vehicle to go 170 miles in 30 minutes. He's up to about 6 miles a minute, which still isn't anything like the ICE or the fuel cell vehicle. But he's pushed it to a limit, and wants to go a little bit further. So that makes the battery electric vehicle not just a city vehicle.
Correct.
And like I say, when I first started doing this seminar, I actually had a slide in there that I really liked from Charlie Freese's presentation, except it had that on it, and I didn't want to say that because it's no longer true.
Yeah.
This field is changing fast, and I mean, 10 years ago, we did not think you could fast charge a battery like that, that it would ruin it if you did it over and over again. But that doesn't seem to be the case right now. So even though we're talking about fuel cell electric vehicles, and we don't want to be there, there are people that just are very negative the fuel cell people are negative on batteries and the battery people are negative on fuel cells. And stop, you're both right. You know, both vehicles have a market, and both vehicles are getting better. But in respect to this range problem or this speed problem, the battery electric vehicle is not just going to be a city vehicle, and that's already pretty much being proven, and it's moving further and further into being able to go, you know, further and further by fast charging.
You know, and one of the statements that Elon Musk had made in one of his presentations that I attended, he also had made the comment that he doesn't want to have a car that will go over 300 miles on a battery charge because the human kidney starts getting damaged if it's not relieved at that period. So we're also looking at the human factor here, that your body will have breakdown points here if you're in that car for that long period of time. So when we started doing fueling stations in California, they started saying, well, if this car goes this distance, we need a station. If this car is going this distance, we need a station. So we're putting stations in with supermarkets or quick stop markets and things like that. So people do have, you know, restaurants and things like that, that they can go and have a meal or go have, you know, their physical needs. So that has also been taken into consideration as this infrastructure has been put in place.
Good point. You know, gentlemen, we're perfectly on time today. If you don't mind, we're going to take one or two more questions, but first, I'd like to ask our participants if they would participate in a survey that helps us improve these webinars and demonstrate our impact to our funder, the National Science Foundation. So right on your screen right now, I'm going to launch this survey. Now, not every computer handles this the same way. You might actually have to click on the link yourself and then click on Browse To. But for many of our participants, my test machines are showing this, the survey is opened up. And if you would just take a few minutes to answer these questions, it will help us. So, John and Nelson, while the participants are doing their surveys, and thank them for it, let me ask you this question, and we sort of circled around it. It's this question of infrastructure. So during the course of this webinar, I have to admit, I jumped on a browser window and opened up the Honda Clarity site to see if they were available here in Arizona. It says they're coming in late 2016, but it didn't say Arizona. So I went on to the hydrogen fueling station sites for Arizona, and it listed none. So am I out of luck, or is there some long-range plan for hydrogen fueling beyond California? Nelson, maybe you know something about that, but do I have a hope here living in Phoenix or many people in other parts of the country don't have hydrogen fueling stations yet? What's your thoughts about that sort of infrastructure and my ability to purchase a Clarity here in Phoenix? Tough question.
Very tough.
What do you think, Nelson? You got any comments there? John, do we lose Nelson there for a moment?
I let him know. I don't see him come back up here.
Can you hear me again?
Oh, there he is. Yeah, hi,
When
Nelson.
When I clicked on that link, I kind of lost you. I heard the question, and basically, I think the answer is going to come from California and how successful Toyota is. Toyota believes in this, and they've stated that their ultimate vehicle will be the fuel cell electric vehicle, and they don't necessarily believe that it's going to be a battery vehicle, almost like that GM slide. And we'll see how that goes. I mean, that slide that showed over half the vehicles in 2050, I guess I would answer this by saying the other day, my wife was reading a fairy tale to my granddaughter, and my granddaughter said, "Grandma, do all fairy tales start with once upon a time?" And she said, "No, no, no. They start with if I am elected." So, I mean, it's politics. You know, if this is driven by government regulation and people don't like the vehicles, there's going to be a problem. So the states right now, you mentioned Phoenix, that are really believe in the California route to clean air and to sustainability and to reducing the increasing carbon dioxide levels and their effects are in the Northeast right now. I think there's 9 other states that are joining California, maybe Oregon also, or Washington. I can't remember which.
Yeah,
But
Oregon.
Oregon. So if it's successful in California, and I think it will be, then other places will follow. But I mean, here in Michigan, it's just we don't have any fueling stations right now. We used to have several, and I mean, a GM was so disappointing. We had one at GM, Ford had one, DTE had one. I think there were 4 or 5 in the area, and you could actually drive from where I live over to Milford, where the proving ground was, and fuel halfway there at the DTE station, which was a 350 bar station, and that's all gone now. So, as I said in the beginning, if 2 years ago, I think I would probably not have wanted to even give this seminar, other than just the electrochemistry, and it's kind of an interesting system. It has some real differences from a battery in terms of how it keeps being fed by the reactants, blah blah blah, but not thinking that this was alive. It seemed dead, but it's not. It's very much alive in California. It's very much part of their political system and their bills and their beliefs. And so it'll be very interesting to see how this plays out. There's reason to be optimistic.
And I also want to point out that with the politics that are behind that, you have the Department of Energy, Department of Transportation, Federal Transit Administration. They just funded 20 transit providers in 13 states to go to low or no zero emission buses. With that funding becomes infrastructure in place. So as these states start to get it, like Ohio's getting theirs this year, you'll start getting retails and public stations coming out. Now, I'm looking at the list here, and unfortunately, no, Arizona has nothing. But I have Montana, Oregon, South Carolina, New York, Delaware, Florida, Illinois, Kentucky, Louisiana. These all got funding for these infrastructures already.
Well, there's some hope there. Thank you. Question for you, John, regarding the education side. I know the hands-on aspects of these education and training programs are critical, but are you aware of any online courses that can help a student get a leg up in this area? Do you offer any at your college, or are you aware of any?
I don't at this time offer any online, and they are being developed through the NSF grant. We're hoping to have some entry-level or fundamental courses online sometime in the next year. But again, we're looking at a technician that's a hands-on person. They have to touch it, they have to feel it, and that's how they work. That's how they understand things. I just noticed one of the questions that came up also here about the safety of the fuel cell storage tanks of the cars. I'm sure everybody that's in this industry has seen the mass destruction video that was done here in Long Beach for the CNG tanks back in the early 70s. The fuel cell tank structures, these things are rated for 26,000 psi. They're 85 thousandths thicker than a standard CNG tank. So whereas a CNG tank, the only thing that will impregnate Type 3 tank is going to be an armor-piercing bullet. Even the armor-piercing bullet doesn't impregnate this tank because of the construction of it. It's carbon fiber. It's wrapped in various layers at different paths, I guess you would say, cross width and diagonally. So the infrastructure of the tank is much more rigorous, I would say, than a CNG tank, even at that point. Whereas you look at a gasoline fuel tank that's in a common car that we're driving right now, they're only rated for 4.5 pounds of impact. A gasoline tank, it's a ticking bomb ready to go off. At 4.5 pounds, that's a wet newspaper at 70 miles an hour. That could virtually crack your tank. These tanks have gone through a lot of testing, and I personally feel safer with one of those tanks behind me than I would a gasoline tank.
I see a question on Next Energy.
Yeah, you know about that, don't you, in your area there, Nelson?
I don't know if that's open or not. I doubt it. I never refueled there. I never, but I think they did have a hydrogen station back in the day, and I'm pretty sure GM probably still has one at Milford. It's just that there was nothing in it when I left in 2012. It wasn't being used.
All right, so some uncertainty there in that one. Well, thanks for responding to that. Ladies and gentlemen, and our presenters, John and Nelson, thank you very much. This has been fascinating. You know, Nelson, my own background is chemistry, and I love looking at those oxidation reduction reactions, thinking about catalysis and membranes and stuff like that. I'm sort of a
One
gearhead.
final word on that. I actually learned that in high school chemistry. I mean, that's very basic chemistry and that electromotive series. If you take chemistry in high school and physics in high school, you'll have a very good start on understanding this,
Sure.
the STEM part of this.
Sure. Excellent.
And that again, we're taking that STEM piece and moving it into the technology with the computers and all the available stuff that we have now. My students are accepting this technology so quick. It's mind-boggling to me.
Cool.
The students that I had 5 years ago versus the students that I have today, it's a total different mindset. They really accept and challenge technology to make sure that they understand what's going on.
It's great, and again, I thank you both. I mean, the presentation was had its very strong technical aspects, but also talked about everything from the social political side, and then importantly to the education side on what our students need to enter this emerging workforce. So thank you both, and thank you for the Center for Advanced Automotive Technology for presenting this webinar. Again, colleagues online, we will be sending out these slides. We will send out the recording, so you'll have all of this information. I invite you to take up Nelson's offer to visit the CAAT website, look for some of their curricular material, as well as their opportunities to participate in their conferences. Nelson, thank you very much. John, appreciate your time out of your busy school schedule in presenting today.
Thank you, Mike. Thank you, John, and thank you for everyone that attended.
All right, everyone, this officially ends our webinar for today. Thank you very much. Goodbye.
Thank you.
Bye-bye.